Hello everyone. Good evening to all. I am Shiv Prakash, research scholar, Department of Electrical Engineering, IIT PH. Let's start the session. It is screen is visible to all.
Yes, sir.
Okay. Thank Let's start the question. This one is first question. For the figure shown below, the on time of the fixed frequency pulse in microseconds. Okay. Here is a comparator. Reference signal is 0.3 volt and modulation signal is 3 volt. When the reference signal is greater than the modulation signal, the output is high. This means let's take this one A, this one B. If A signal is greater than B, then output is high. If less than B, then output is low. Here asked the on time. What is the on time of this signal? Draw the signal in one waveform. This one is VA. Second one, oh sorry, this one VB, this one is VA. The total time period is 2 microseconds. If we observe that this one output signal, then output will come when VA is greater than the VA. That means this one will come into out. He has this time period aunt T on. Okay, this one is 3 volt and this one 0.3 volt. If you observe that M1 means slope is y-axis divided by x-axis. It's a total 0 to 3 volt divided by total time period 2 microsecond, 3 by 2. So what is time or is signal goes behind beyond the 0.3 volt is the on time. This means we observe the 2 microsecond, we go to 3 volt. This is 1 volt, go 2 to 3 microsecond, then 0.3 volt. When we go 2 by 3 into 2.3, I think 0.2 microsecond. This one is the on time. T on is equal to 0.2 microsecond. The second question, a buck converter is operating with a constant on time control. In this record, which of the following is true? Is that true means it's one option true. So it is 0.4 volt. Yeah, you can say, I think I taken the 0.3 volt and 3 volt. That's why it come 0.2 volt. Same process you can apply for a 4 volt and 0.4 volt. So no matter. The buck converter, you know about the buck converter very well. This is it. Diode. C, D, D. This one V naught. It says the ripple current is maximum. First person, ripple current maximum at maximum input voltage. Okay, okay, it's first. It's okay. It says that 2 microsecond go 3 volt. That's why 1 volt is 3.2 microsecond. Given what will time take to go is the 0.3 volt. You know the ripple current in the buck converter is given the on time control. It means on time control is not defined as the fixed frequency. It can vary the frequency. That's why this option will not correct. On time control and it is not given the off time control also. If you on off both are controlled, then it fix the frequency hyphen. And if only on time you control, then off time not control, then frequency can vary. The ripple current, you know about the ripple current, del IL. When you take a first, then you find V in minus switch is on cycle, V naught divided by L into T on. Here is give the T on is constant. If T on constant, this one constant, output voltage also constant, L again by design, and it is also constant. Then it will input voltage, if input voltage will increase, then delta IL also increase. That's why first question is correct. Now the inductor current ripple is independent of the voltage. No, it is depend on the input voltage. It's no wrong. Voltage ripple is maximum at maximum input voltage. You know about the voltage ripple? Delta VC 1/2 delta IL the total time period. I think 1 second. 2 by 2. If you observe this one IL, same current flow IC, but average current will 0. Then you obtain the charge. You can, this one is charge the capacitor, this one discharge the capacitor. This time period, total time period is T. Then I think this one goes behind before that. This one is 0. This one is T. This time period you observe T by 2. Total time period T by 4, and half is discharge and half is charge. That means the capacitor the charge balance. Then you find the delta Vc. Actually, Q is equal to Cv, and del Q is equal to C delta V. So find del V is equal to del Q by C. Del Q is means it's a charge time or discharge time. Change the 0 to charge time or charge time to discharge. Then you find this total is delta IL, then half on delta IL by 2, and you find triangle 1 by 2 delta IL into total bits T by 2. This will it here. Delta Vc 1 by 8, can write T is equal to Fc. Delta IL I will find that V in minus V naught 12 into T on. T on fix the delta Vc says that ripple voltage is maximum at maximum input voltage. We observe when the input voltage maximum increase, then delta Vc also increased. Yeah, that's why I think first and last both are correct in this question. The third one, another pulse width modulation in this continuous conduction mode are a conventional buck converter. When load current decreases from 10 ampere to 3 ampere, then what will be the percentage change of duty ratio and switching time period? In pulse width modulation technique, the switching frequency is fixed. Switching frequency is changing the frequency modulation technique. But here we taken the pulse width modulation technique, which means here frequency, switching frequency is fixed, means time period is fixed. Then can B, can C option true here. But for that you drive the equation. No buck converter in this continuous conduction mode. This will happen in IL, inductor current. This one IL maximum. I take this notation dt raised to dt time period and d dash and this one d double dash total time t. If you take a circuit, then you find when switch is on, then VL, this one VL, inductor voltage is Vs minus V naught, and when switch is off, then you observe VL is equal to, diode is on, that's why VL is equal to minus V naught. You can apply the Bolt second valence equation, then you find VL dt plus VL d dash d plus VL d double dash d. Actually, in d double dash condition, VL is 0. Here you observe that d double dash condition, current is 0, voltage is also 0. Total time period is equal to 0. VL is equal to Vs minus V naught into d plus this time period minus V naught into d dash. Actually, t cancel out to all of, then you can d dash is equal to 0, and d dash is equal to Vs minus V naught divided by V naught. Sorry. After that, you know the average inductor current is equal to output current. Then in this triangle, you find the average of this. Then you find the output current or inductor average current. This means half and peak current or height of the triangle IL max into total time d plus d dash t and total time period. They cancel out. Then you find I naught is equal to half IL max into d plus d dash. This one equation number first, this one equation number second. You can also find here the IL peak. If you observe the first condition, when switch is on, then voltage across the inductor is Vs minus V naught. Then VL is equal to Vs minus V naught. Switch is on. Then VL will written as del L di upon dt equal to Vs minus V naught L di L Vs minus V naught divided by L into dt. You integrate the both from in discontinuous conduction 0 to IL max inductor, 0 to IL max, and he is go from 0 to d, 0 to dt. You solve this, you will find IL max is equal to Vs minus V naught divided by L into dt. put IL max into here. Then you find I naught is equal to half into Vs minus V naught divided by L into dt into d plus d dash. Put 2 I naught into L here, Vs minus V naught to dt to d plus d naught d dash fixed from equation number first. Then you find Vs, I think this one into d, sorry, missing there, minus V naught divided by V naught into d. If you solve this, you find 2 V naught I naught into L is equal to V naught cancel out, Vs to Vs minus V naught into d square into d. We observe this equation, equation number 3. Then you find d square directly proportional to I naught here. Written here. Then d square directly proportional to I naught. It means d directly proportional to root of I naught. Here says that current is decreased from 10 ampere to 3 ampere. Then you apply here. Yes. Then you apply d2 d1 ratio I naught to 2 I naught 1. Here is given in I naught 2 is equal to 3, I naught 1 is equal to 10. Then we find d2, we solve this 0.547 to d1 approximately 0.55 d1. Yes. Then what percentage change means d2 percentage change is d1 minus d2 divided by d1. With respect to d1 you will find, then you can 1 minus 0.55 d1 divided by d1, you know that 45% d2 will change. D2 ratio will change 45%. Here option reduce, okay, is not increase. D2 is 0.55 d1 only. The second, for fourth question, if PWM regulated conventional boost converter in the inductor current ripple become maximum when? In boost converter, draw the circuit first. This is the ripple current. Same apply. Previous page, okay. I think this one. It's okay. I got next question. Here is in the boost converter. PWM. Then first you find the delta IL, and switch is on first condition. Then you find VL is equal to VS. That's known as DIL upon DT equal to VS. Yes, you can watch later on YouTube also. I uploaded this video on YouTube. I send you link channel. Thus you apply here LDIL is equal to VS into DT. Same as you integrate, like is the continuous conduction mode. If it is not given the boost converter or discontinuous, then you can observe this one continuous conduction. Then IL will change on I minimum to I maximum. Del IL is equal to Vs by L, integrate from 0 to dt. Then you find IL max minus IL minimum is equal to delta IL. Delta IL is equal to Vs into dt divided by L. You also know the bar for boost converter V naught is equal to Vs divided by 1 minus d. You find Vs is equal to 1 minus d into V naught. Apply here, and delta IL is equal to d into 1 minus t into V naught divided by L. You can change FL. And let the equation is equal to y. You differentiate these ones, dy by dt for maximum. See the maximum equal maximum when respect to dt ratio in d. Then you find 1 minus 2d into V naught divided by S Guru Prasad. FL. For the maximum, find the maximum principal, you whether equal to 0, you find here d is equal to 1 by 2, it means 0 0.5. If you find 0 0.5, then you put here out, you find Vs is equal to 1 minus d into V naught, and d is equal to 0.5 to take 0 0.5 into V naught is the answer. Vs is so V option. So okay, this question number 5. For the inductor current waveform shown in figure, the RMS value of this waveform. If you know the RMS value, you can solve the problem from taking the slope of both train line, charging discharging current, and you can also apply for the same. You find RMS direct formula I drive here, 1 by T. Let this one x1, this one x2, x3, x1 square plus x1 into x2, x2 square divided by 3 into this time t1, t1 plus x2 square plus x2 into x3 plus x3 square divided by 3 into t2 this time. Total time period is 8 by 8. x1 is 0, it means 0 plus is also 0, x2 is equal to 4, this means 16 divided by 3 into this one is 4 plus x2 is 16 plus x3 is 0, this means 0, this one 0 divided by 3 into t2 is equal to given as 4 minus 6 minus 4 is 2. And find I RMS is equal to 1 by 8 16 into 4 divided by 3 plus 16 into 2 divided by 3 divided by 4 8 to all 2 into 4 divided by 3 2 into 2 divided by 3 this one 12 by 3 4 I RMS is equal to 2. So yes, correct. Question number 6. Consider the following figure. Explain once and step in question number 5. I take the right formula for that. Sir has also explained this formula and in this video, but you can also apply the same. You know, if you know the at least second and third step. This one, you're putting the value x1 is equal to 0 and x2 is equal to 4 and x3 also 0. You put there, then you find 16 square of 4 x2, only x2 is find here, and here also x2 is find, and you find that this one 0 16 into 4 divided by 3 and 16 into 2 divided by 3 as divided by 8 to here and 16, and it divided by 16 divided by 8 is 2 into 4 is 2 into 2, then 4 to the 8 plus 2 the 2 4 12 by 3 is equal to 4. RMS is equal to 2 ampere. Is okay? This value given actually x1 x2 I choose the if each corner you can choose the value x1 x2 x3. If someone also here, it means you find this one like that equation, then you find x1 here, x2 here, x3 here, x4 here, and apply same formula for all of them, then you find the RMS value. Each corner you can take one variable. Consider the following below, consider figure below. The rising slope m1 of the sawtooth waveform, because this one was discontinuous, that's why I asked. Okay, but you don't the discontinuous means you can find RMS when your wave is present. Where is wave is present, that's why you can apply only this for RMS value. But the total time period, if you see that, then total time period is starting from the wave from 0 to here. The second waveform will start here. 0 to 8 you can take time period, total time period. You cannot take only 6 is the time period, because of 6 one is this continuous current, but less next wave will start from the 8 second. Then you can take total of 0 to 8 is the time period of this waveform. Here the first slope is 1.5 volt per microsecond, and reference is given is 0.2 volt. Is also comparator. When reference signal is greater than the sawtooth wave, then your output is present, and reference signal is low from the sawtooth wave, then is present, Q is low. Is given the sawtooth wave only given 1 volt is time period, and is saying that after duty ratio of d1, if the slope of sawtooth wave is increased 2 volt per microsecond, then to keeping the duty ratio and peak of the sawtooth is same, the new reference voltage is saying that duty ratio is same for both references. First we find the duty ratio. What is duty ratio? If you observe that the slope is equal to 1.5 volt per microsecond. And find 1 volt equal to time period. When 1 volt is goes to 1 volt, then what is the time period of this waveform? You find 1.5 volt is given the 1 microsecond is the slope, then what will time take for 1 volt? Because the time period is 1 volt present for t1. And for 1 volt, 1.5 microsecond, it means 2 by 3 microsecond is the time period. It's t1. T1 is equal to 2 by 3 microsecond. You find d1 also. If this slope is given, same you can apply for 2 volt, 0.2 volt. You apply 0.2 volt, you find 1.1.5 volt into also to 0.2. 2 by 50 microsecond is the d1. Next it says that slope is increased to 2 volt per microsecond. Then what is keeping x constant, the voltage reference voltage is asked. Slope 1. Okay. Oh, sorry. Like 2 volt per 1 microsecond. Then 7 and 2 T1 into T1. Mhm. In 1 microsecond. So yeah, 1 microsecond is 0.2 volt. Then 2 by 15 microsecond, you can find 2 by 15 into 2, 4 volt by 15. Actually, so this one D1 is given, and D1 is equal to 2 by 15 divided by T1, 2 by 3, 1 by 5. This one is constant. If you find here slope from the slope, find time first to find time period. If slope is 2 volt per microsecond, then time period is 1 by 2 is equal to T2. Then you find D1 into T2, the total on time. D1 is equal to 1 by 5 and T2 is equal to 1 by 2, is equal to 1 by 10. Then you find this one. And T1 D1 is the on time. Then you find in 1 microsecond and 2 volt, and 1 by 10 microsecond. You find 2 into 1 by 10, so 0.2 volt is the difference is same for this also. If you increase the voltage, then frequency is increased. That's why difference voltage is same here. I think same. V reference to also 0.2 volt. Next question number 7. Under the constant on time modulation in this continuous conduction mode for a conventional buck converter, when load current decreases from I0 1 to I0 2, then which of the following waveform is correct for a given input voltage? I think V in V0 T on L is the fixed, is the given input. This quantity is fixed. An option is given here. First, the I peak is greater than I peak 2. It's been you observe that he says that T on time is fixed. It didn't cast is continuous condition T on is fixed, it means this peak is also fixed for both. Then this one not correct. I peak is equal to I peak 2, because of T on is fixed, then current inductor is increased. Because of L di upon dt, L is fixed, then current T on will also fix, then current is going to peak is same for both the cases. Then first one is not correct, second one and third one also not correct. First not correct, second B and D. In this you B or D can have answer, but I solved it. I want to solve this. Waveform is given like that, 0. This one I peak, T. T on, this one T off, can take this one T. If this one is fixed, it means if you want to decrease the average current of this, then you should have increased the off time period or increase the frequency. Yeah, increase the time period. Sorry, time period is increased, then peak total average of this waveform also decreases here. But I want to solve this according to, if you find this one M1, this one M2, you know the M1 is equal to Vs minus V naught divided by L in buck converter, and M2 is equal to minus V over L. You can apply the here whole second equation, then you find this voltage. This one voltage is and switch is in arm on, then Vs minus V naught I written directly to T on minus V naught by L into T off should be 0 for the voltage second balance equation. So here T is equal to 0, then we find here T off Vs minus V naught divided by V naught into T off. Find IL, and you apply the here triangle 1 by 2 into total I peak to T on is T off divided by total time period T. And also you can find here for the I peak you apply DIL divided by dt to Vs minus V naught when the switch is on period. Then we have 5 find I peak is equal to Vs minus V naught divided by L into T on. Put T on here. IL average equal to Y naught 1 by 2 t I peak is equal to Vs minus V naught divided by L to T on plus T off T on plus T off. You can find here T off is equal to Vs minus V naught to T on plus Vs minus V naught divided by V naught to T on to TL into I naught. Sorry, I had to press here. To find take T on square. V naught cancel out T. If you observe T on is fixed, Vs V naught is fixed, L fixed, then you find T directly proportional to 1 by I naught. Y naught is decreased, it means time period is increased. Here, yes, time period is increased. In day also, time period is decreased. This is incorrect. Yes. Question number 8. An ideal DC-DC converter is shown in the figure, but all losses being ignored. In this one, buck boost converter, due to ratio, take the switching frequency, then that critical value of the load resistance and DC conversion ratio V naught by V in of the converter applying this continuous connection. So this here, this continuous conduction mode, you apply this continuous same waveform find for IL. This one D, this one D double D dash, take D double dash for the boost converter. IL max. But critical condition, you know about that. I naught on a delta I naught by 2 should be greater than 0 for continuous conduction mode and equal to 0 for critical condition, and less than 0 for discontinuous conduction. Here as the resistance at critical resistance, it means this one value I naught, you know I naught a average of this one. If you find the in critical condition, then this one is the critical condition waveform of IL, and average of this is I naught, I max, total is the delta IL. If a delta IL by 2 less than this, we do so delta IL by I naught is minus this one, half is less than this one, then we go for discontinuous condition. This time is the del I naught is equal to delta IL by 2. I can say that IL both for, but they are not boost, is the boost converter, then you can apply this one. delta IL find from this equation. This is when the switch is on, then VL is equal to V in first condition. L di by dt V in, we find the DIL here. For same we apply the integration both V in divided by L into dt. Sorry, this is not IL for boost converter, this is I not for the buck converter. So IL for the boost converter actually, average current of the inductor. Because of the boost converter, average current of inductor current is not equal to the output current. In buck converter, inductor current, average inductor current is equal to I not current. That's why I only IL. If you take the whole second equation, then you find for the critical condition V naught is equal to same as a continuous conduction motor is a continuous conduction mode. V as 1 minus T is not for the discontinuous, here only for the critical or continuous conduction mode, where D is the critical value. But we will find the current second equation means inductor current here. Apply inductor current. In first condition, inductor current is equal to minus I naught here, and when the switch is off, then inductor current is IL minus I naught. And take here IC T on plus IC T off is equal to 0. When switch is on, then this current flow like that, and IC flow like minus I naught V naught by R minus V naught by R T naught means dt plus IC at T off condition IL minus V naught by R Y naught into 1 minus D equal to 0. So it divided by T total as the average current. T cancel out. Find the average current 1 minus D minus V naught by R plus D V naught by R minus this one minus V naught by R into D is equal to 0. Cancel out. We find IL is equal to V naught by R into 1 minus D. It means we put here, sorry, put here IL is equal to here from this equation. A critical condition IL is equal to delta IL divided by 2, and IL is equal to V naught divided by R 1 minus D. Delta IL put here into dt. You can change V in from here 1 minus D minus d v in dt divided by L. So v in minus d into v output. Now v in is equal to vs. V naught will also cancel out. Delta L by 2, I think. 2L by R d L by R RC here. Oh, for V naught I have not spaced that, then oh, sorry. You can see in the lecture YouTube also I uploaded this, then you can find all of this. For second portion, V naught by V in, we take this diagram and same apply the both second equation. Then we find VL into D plus VL into D dash plus VL to D double dash equal to 0. Because D double dash is equal to also 0 because of voltage current not present here and voltage also 0. And VL when the switch is on, V in to D plus VL and D off is equal to same as V naught. This one is equal to 0. And find D dash equal to dV in divided by minus. Second, we find the I naught. Actually, when the switch is off, then this waveform is presented I naught. Because of when the switch is off, then same inductor current passing through the load, and average of this current is equal to I naught. Then you find I naught is equal to this one on the area of this rectangle I max into time period T dash into T divided by total T. T cancel out. Question number first and question number second. You can also find the IL max. For here, you apply V in by L into dt. When switch is on. put it here. I naught is equal to 1 by 2 into IL max V in divided by L into dt d dash is equal to d V in divided by V naught equals I naught is equal to V naught by R into V in divided by 2L into d square by V naught then you find V naught by V in square is equal to root of V square t also present here. Okay. Yes, this one. Sorry, V naught square so to say V naught by V in to minus here also minus t square tr divided by 12 take as the magnitude then minus cancel out then you find whenever go r is equal to downside then you find same as 2l divided by rt is w then the option I think correct. So question number 9. The DC-DC converter shown in the figure such frequency is given is the 100 kilohertz and inductor also given 2 microhenry. Duty cycle of operation MOSFET duty cycle also given. Then yeah, so output capacitance of C required to keep the peak to peak in output voltage equal 1%. And delta V naught is given to take 1%. You know about the delta V naught is equal to VC here. You can find. Here is the buck converter. Buck converter, you know about the buck converter. Delta VC 1 by 8 d 1 minus d V naught divided by F square L C. Maybe put in formula this C and d 1 minus d V naught divided by F square L into delta VC. Put formula 0.5 V naught is 8 F square also given 100 kilohertz L also given 2 microhenry and delta VC V is given 1%. Put value here 1%, then you find calculate the all of things and 112.5 microfarad. Simple calculation, you can calculate this. Question number 10 here. Here the boost converter. The output voltage of the DC converter shown in the figure to be regulated at 48 volt It means output voltage is given 48 volt, V naught is equal to 48, V in given 20 to 30 volt, load resistance also given 12 ohm, Fs is also given 100 kilohertz. The value of inductance required to limit the maximum allowable inductor current ripple delta IL equal to 10%, 10% of I naught. Find the inductor. First of all, you find the I naught. I naught is equal to V naught by R. V naught is equal to 48 by R is 12, 4 ampere. 10% of 4 ampere is 3.4 delta IL. Also given the maximum allowable inductor current ripple. We know delta IL is equal to D1 minus D V naught divided by FF. In maximum, it is maximum when the D ratio is, and can also change for the 1 minus D Vs divided by FL. Duty ratio is minimum and Vs maximum. And Vs V in maximum, then also duty ratio is minimum. Then you find the delta IL. Maximum 10% is given, and 1 minus D minimum and Vs maximum. Put the value, find L. We calculate this, all of things given. D minimum we find by the apply output voltage. Sorry, not buck converter. But I think boost converter. You can find delta IL for boost converter dVs upon L. And D minimum for boost converter, you know Vs is equal to V naught is equal to Vs divided by 1 minus D, and find D into 1 minus D V. Take D is minimum. For this value we have maximum V naught given out, and find uh, 1 minus T is equal to Vs divided by V naught, and D is equal to 1 V output minus Vs divided by V naught. The minimum value also required for the limit the maximum level inductor current. Okay. we will find the minimum value. Take the output minus V is maximum 30. Find this and put this here, then you find A is equal to D1 minus D0 delta IL so given 0.4 into F and find the answer of 125.7. If you have any confusion, then this video is uploaded after YouTube. You can search from there. I provide you a link here. Just wait something. The efficiency is very high. And here is channel link and search and see the video first second also. Okay everyone, I will stop the video here.